it, they do say a lot of very good things. And one of the things that maybe, I mean, is an overall impression that you can get out of that is that there's a huge difference in construction and design with concrete as opposed to a material like steel. Steel, there's not too many ways you can screw it up. And fortunately, when you screw it up, you can usually correct it. I mean, if you're putting together a steel structure, what can you do? Leave a bolt out or something? Well, it's very easy to inspect and see that it's wrong and correct it, as opposed to concrete that's usually harder to inspect. There are methods, by the way, to non-destructive methods to test it. Once it's in place, a Schmidt hammer is one where you have a little device that you knock against it and it measures the density. Sometimes it's X-rayed or something, but you get an idea even in place of the strength. But if there's a problem, man, that's not so easy to correct. And you can see there are a lot of ways. I mean, when you think of that film and the description of it, oh, let's see, you know, I bet I don't have this turned on. Not that it matters. See if that's on. Is it on the podium? It'll probably explode now. There are a lot. Whew, yeah, now it's on. There are a lot of things from the design of the mix, the batching, the placement, the curing that impact the final strength. So it's not. That's another big difference with steel. You specify, you know, the ASTM grade of steel, and unless somebody screws up, that's what you get. You get that strength at the site. With concrete, there are many more places where it can screw up. First, you have to specify the right concrete. Then it has to be actually produced correctly, batched correctly. The ingredients have to be properly proportioned. The transport has to be correct, that it has to be those trucks that you know, tumble the concrete, they go at a certain speed and a certain number of revolutions. And once it leaves the plant, usually the water's added at the plant and it starts mixing as it goes. I mean, there's a clock that's ticking when as soon as the water hits that cement. And it's a chemical reaction. It's like, you can think of it as a slow reaction compared to acrylic, but if you've ever worked with polyester, you know, that or epoxy, you know, that you have that concept. You mix the two things together and you stir it up, and by golly, you've got like 30 seconds to do something with it, or it's going to be hard in the cup, you know. And then you, okay, well, that's it. Well, concrete's the same thing, only it's a little bit longer. You maybe have an hour or something, or whatever the time is, depending on the type of concrete and the way it's been batched. But there is a clock that's ticking. And there's one of the critical points is when that truck arrives at the site. Unlike steel, you know, you deliver, the truck arrives at the site and they just pile it up, you know. I mean, eventually they put it up. But concrete, that truck arrives and everybody's got to be ready to go. Your crew has to be, they can't be sitting there eating lunch and saying, well, I've still got 2 bologna sandwiches to go. You know, when that truck gets there, you've got to have people ready. And sometimes that is the architect. I mean, I've been in that position where I've got to get the guys, come on, it's time. And if it's a good crew, I mean, they realize that. But you know, that is part of what gives concrete its you know, the quality. And it's got to be placed and placed properly. Then you can screw it up in placing it. You saw with the vibrators, you can properly vibrate or you can improperly vibrate by dragging the thing along. And what happens is, or over vibrate. The vibration is to get the air voids out. But if you over vibrate, it separates it. Suddenly you get rocks at the bottom and goo at the top, and that's trash. Or, you know, all the other things. I'll post that, I think, somehow. I'll post that, and you might even want to download it and look at it yourself one more time through, because it is a valuable video. They say a lot of, I think, on the level of of what you'll probably be in contact with if you ever, are at a site or if you're involved in a concrete design. I mean, just the realization that there are so many factors that impact the strength. Then what was the other one they talked about? The location in terms of the temperature impacts the chemical process. Obviously, since it has water in it, my goodness, if it freezes, you've had it. The thing's going to get ice crystals. Water is one of the few things on this planet that when it gets cold, it gets bigger. When you think about that, almost everything else, it gets cold, it gets smaller. But water, it gets cold, it gets bigger. It freezes, ice is bigger than water, or liquid, right? It gets bigger. And this is the problem if you have something cast with it, it expands because it's ice, and then when the ice thaws, then it's trash. You've got cracks all through it. Anyway, well, I won't repeat it all, but we will talk a little bit about it and about the constituent parts. This is a little chunk, and you can pass this around. There's a couple things you can observe about this. I'll pretend that I'm observing. I can't see it because I don't have my glasses on, but I believe what I'm looking at here is this was taken out of a exterior slab. It was a core sample that was pulled out. And this is an example that does have some air and training in it. And you can see what air and training is. It's not big bubbles. Actually, the air and train bubbles, they're in the visible range, I guess, but they're not very big. I mean, you could see them better if you had a magnifying glass. They're little tiny bubbles. But those little bubbles are very important to exterior grade concrete, right? The air and training they talked about. The sidewalk in Chicago is not like the sidewalk in Florida. I don't even want to say the word. Because when that goes through a freeze-thaw cycle, those little tiny bubbles give the ice someplace to go. If the bubbles aren't there, the ice just cracks the interior pore water, cracks the concrete. So you can get an idea of what the big bubbles that you see here, those are mistakes. It's the little tiny bubbles that you can barely see. Those are air entrainment. The other thing you can look at this, look at the aggregate. It's not all the same size. It's not like they just dump rocks in there. There are carefully proportioned sizes of rocks. Aggregate in concrete is graded, meaning that there is a proportion from very fine rocks to very coarse rocks. Here, you can pass that around. And the reason is to get a denser mix, a denser aggregate. If you had something to measure with, a bucket, and you filled it full of gravel, and the gravel was all exactly the same size, let's say. Oops, it's hard to draw gravel the same size. Okay, well, there would be a certain solid void ratio here, a certain ratio of the rocks to the voids. If you take the same thing and do it with smaller rocks, it would take a lot longer to draw. And you could be here for a while, but eventually you'd get the idea. You'd fill it up. What would that do to the solid void ratio? Would the solid void ratio go up or down? And let's see, would I have more solids? If I weighed these two, right? Because the air doesn't weigh anything. Let's say I just fill it with. Which one's going to be heavier? That sounded like agreement. Would you believe if you have really, it's just a matter of scale. These should weigh the same thing. And if I have another beaker and I fill it full of sand, it also weighs the same thing. If it's the same, say it's all limestone. Limestone 1.5 inch, 3/4 inch, and then manufactured well, no, not manufactured, non-graded sand that's all the same size. If all those three are the same size, it's just a matter of scale. It's just, come on, it's like you drew it and then you hit this, scale command, you make it bigger. But making it bigger, you've made the voids as big as it all scales together, right? The solids and the voids. So the proportion of solids to voids stays the same. You've just changed the scale. So if you have all the same size rocks, you're going to have a set solid void ratio, and you're not going to be able to change it. But if you had this bucket, the voids would be bigger because you've scaled. This is a bigger scale, right? So you could take some of these little ones and put them in here. Look at this. Now you're adding rocks to it. Of course, it's going to get heavier. It's getting denser. And you could not only add this size, you could throw in a little sand. Oh, and that would fill in the other little holes. So you can, by proper grading, a scale of and this is also for the sand. The sand that you use in concrete. There should be another slide here. Talk for 10 minutes and forget to push the buttons. There we go. The sand that you use in concrete is not like the sand that you know and love from your sandbox at home. That's sand, beach sand, if you will. That's non-graded. It means it's all the same size, right? It's all the same, more or less. That's all the same size. So if you use that kind of sand, then you'd have the same problem, at a different scale. Then you wouldn't have, so you want that gradation of aggregate, this and this, even to apply at the sand level. And concrete sand, it's called manufactured sand or graded sand. It goes from very fines, kind of dusty stuff almost, down to, or up to, depending on the way you think about it, quarter-inch aggregate. So from quarter-inch all the way to fines would be a mix of concrete-type sand, not beach sand. You do use non-graded sand in mortar mixes for a very different reason, because it being all the same size, it makes it much more workable. You can spread it like peanut butter, without the nuts. Everybody knows crunchy does not spread as nicely as smooth. Well, so you get all the same size sand, and it spreads a lot smoother, and that workability is more important than the strength for mortar. But for concrete, that's not quite so. You want the strength, so that grading's very important. What else here? Turn those lights off. Let's look at these lovely pictures. Okay, so this just to say, kind of reiterate the things that go into it. Sand, this is together is aggregate really. Sand is an aggregate too, but you separate it out usually. This isn't the world's best picture of it, but this is all crushed limestone. All these are the same material, and this is the crushed limestone is pretty good for aggregate because it has a good density. It's not friable. It doesn't come apart. It's strong, and it's angular. When you crush it, it's kind of got very irregular shape, which means in the concrete it kind of keys in physically and makes it denser. Even dry. This is true. If you took, this is why it's maybe a little naive, you've probably driven on it. You buy a rock for your driveway, you get like probably 1 inch or maybe 3/4 inch crushed limestone. You put it down there, you compact that, smooth it out, and you can drive over it quite a bit, and it's not mushy because because of the irregular shape, it kind of locks together. If you get river rock, that's dredged out of a river, it's round. It looks pretty, right? It's kind of polishy looking, has nice colors. Also, it's very hard. It has a lot of quartz in it usually, but the smoothness does not mechanically locked together. And if you have it in a driveway and you drive across it, your tires mush down. You walk across it and you kind of your feet, or you ever walked across pea gravel, right? You have a pea gravel walk, your feet kind of mush into it a little bit. Anyway, well, you can pay attention to the world you step on, So that's an advantage of this crushed rock. Also, you get an idea of the grading. Usually in architectural stuff, because of the size of the members and the placement of the bars, you know, 1 inch, 3/4 inch, something like that's probably the maximum size. If it's a really big member, you might get a little bit bigger. Aggregate like this is, I don't know for sure what this is, but it looks like 1.5 to me. That's definitely a pretty large piece. Anyway, that might be for a larger road construction, or it might be for, I don't know, some larger casting. So this is 3/8. This is kind of small. So somewhere in between here is probably the maximum size for architectural use. All right, cement. Yeah, that's a sack of cement, in case you haven't seen one. 94 pounds, I think, or somewhere. I don't know why there's such an odd. Oh, I think it's. What is it? There's a reason why it's 94 pounds. I don't remember what it is now. It's how it proportions with mixing by hand, I think, and fits in things. Anyway, these are the different types. This is the common type, whatever, low sulfite. This is the one you use in winter, right? Type 3. So you'd see that around here quite a bit available. Like if you went down to Lowe's, one would guess you could get that off the shelf because we have winter here, This one is the one that's the slow cure. Concrete does produce, if you've ever worked with it, it is a chemical reaction, and the cement reacting with the water does generate heat. There's a hydration. It strips the hydrogen out of the water, breaks that chemical bond, and water is not an easy thing to break in half, so that generates a little bit of heat. And if you've got a lot of cement, there can be a rich or a lean mix proportion amount of cement in the concrete. Right? The cement is not concrete. Concrete is rocks and sand and water and cement. But if you've got if the cement part in your recipe is high, it will generate more heat than a lower ratio. So very rich mixes, you might want to use type 4 to keep the heat down. The problem is if you get it too hot, the whole thing does expand through heat, and then when the heat cools off, it shrinks. I've seen, when I was down in Tennessee, they built some big dams, and I knew some of the people that worked on those, and they said they physically put ice. They mixed it not with water, but they'd mix the concrete with ice, because you're talking about really massive casts that are several yards thick as they cast these big dams. And it generated so much heat that it was a serious problem. They had to somehow reduce the heat. Even with this and reducing the amount of cement and mix, they still had so much heat they were mixing it with ice to try to keep it from generating so much heat. Anyway, okay, so cement, and the last bit, water. The only stipulation with water is they usually say potable, which it doesn't really have to be potable. Means you could drink it. It's not so much that it's potable, it has to be drinking water. It's just you don't want organic trash in it. You don't want leaves and sludge and scum, and you don't want to be scooping the river, some water out of the river. You also don't want stray chemicals in there that you can't control that might degrade, like a lot of salt. You wouldn't want to use salt water. That would be a no-no. Or something like that. But it's usually organic material that you've got to be careful about. Okay, they showed this guy making this, but they didn't quite show it all the way. I wish they would have. This is how you measure workability on the site with a slump cone. And this is done pretty regularly because they're trying to, particularly with a slab, it can be, people are constantly shouting to put more water in it, but you don't want to put more water in it because that degrades the strength, but you do have to keep it workable, and you might have to add either water or add an admixture even on site if the workability drops, because you have to be able to spread it or you're not going to get the product you want. The way this works is it's simply you cast in this little cone, this cone of concrete, and then you lift it up. It's a ASTM procedure. You have to put the cone down, you lift it, you pour in a third of the cone, 28 rods, another third, 28 rods, another third, 28 rods, lift it off, set the cone beside it, like he did. He lifted it off here. Well, he didn't. He has a special thing. Usually, they set the cone beside it. You put this rod across the top of the cone, and then you measure from that rod the amount that the concrete slumps, and that is called the slump measurement. And that slump is used as a gauge of the stiffness. If you have a low slump, like a slump of 1, that would be 1 inch. That means it only dropped an inch. It just went 1 inch. That's not very much. That means there's no way you're going to cast that into a slab. They were talking about that machine. You saw the curb machine. Well, yeah, that takes it practically dry up that conveyor belt, dumps it in a hopper, and presses it into a mold. Okay, a slump of 1 may be okay for that. Precast has very low slump because they pound it into the form practically sometimes, or at any rate they have control over it. But a slab on site, you'd have to have a much higher slump, like 4 to 6 or something. Maybe it says up there, 2 to 6, without vibration. Whatever. If you get too much slump, like maybe beyond 6 inches, then you've got soup. And that's also a bad sign. There's something gone wrong. Somebody put way too much water in it, and you're going to have garbage. You'll have to rip it out, and there's going to be a big problem. So it would be better not even to use it than to go on with it. The biggest thing that affects strength is the water-cement ratio. And they mention that several times, about certainly there was one, I know, when the guy was adding water, a big circle with a no, red, do not do. Yeah, that's one of the things that you have to be very careful about. Even if you were somehow involved in a project and controlling it, people will, it's very tempting to add more water and as a solution to you not working fast enough or somehow not being organized enough. The truck sits there too long, it's starting to harden up. Either you add more water or you dump 9 yards of concrete in your front yard. But if you dump it in what's going to be your driveway, it may be garbage if you add too much water to it. See, so you got these problems of life. But adding water does degrade the strength. That more than anything else. The more water you put in there, the strength is. In fact, there's probably. The other thing, well, I'll say while we're on this, the cement cement content, that's how much cement is in the concrete. Putting more cement in to an extent does usually increase the strength. It's the real binder. But having too much cement in there probably doesn't help because really the rocks are stronger than the paste. The other problem that's probably more critical is the cement costs a lot more than the rocks. So the more cement, the richer the mix is, the more expensive it is. So generally you try to keep this as low as you can for cost reasons, but also but you have to balance it. More cement makes it more workable. Okay, this shows you graphically. Here's water-cement ratio. This is the strength. Right, so you can see as a high water, this is maybe 0.65, the strength is below 1,000. 0.4, it's up over 3,000, so 3 times the strength just by putting in, and that's not a great deal of water difference. Just 0.2 of a whatever that is, of the ratio of the water to the cement. It's not water to concrete. This isn't water to concrete ratio. It's water to cement. And you've got to think the cement is not the biggest constituent of the concrete. So it doesn't take much water to drastically change the behavior of the concrete because it's a water-cement ratio, not water-concrete ratio. So a little bit of water in the mix suddenly changes you on this graph. Changes the workability quite a bit, but it also changes the strength. So as you know, the truck may arrive here, and here's after 2 bologna sandwiches, and then you kick around, and then somebody says, let's add some more water because this is really hard. So the more water you add, your strength is just going down, down, down. Not good. All right, well, that was probably as good a place as any to stop. Monday, you realize there'll be a little examination in here of your intelligence. Hopefully you'll be prepared, right, with a pencil and calculator and 2 cups of coffee behind you, right? Very good, very good.